In order to construct a noise generator with a several volt output, we have to have some original noise to work with. There are several places you can obtain a basic noise signal. I've seen suggestions that you can obtain it from a DC motor, although that has the problem that it doesn't have a flat frequency distribution. I have seen a suggestion that you could simply cascade several operational amplifiers in series with no input to the first one and with fairly high gain on all the stages to just amplify the noise that the op amps themselves generate. If we were doing this digitally, we would probably implement a primitive polynomial using a shift register to generate what is called a maximal length pseudo-random sequence, and this has some advantages, primarily that it actually is repeatable. If you restart the thing from the original state, it will repeat exactly. But that involves digital hardware, and we're doing this with analog stuff. However, the most common means of obtaining a noise signal with a flat distribution with which we can work is to reverse bias a semiconductor junction. In a reverse biased semiconductor junction, unless something dramatic happens, and we'll talk about that in just a minute, there is only a very tiny current flowing through the junction. This is called the reverse saturation current. This current is almost entirely due to thermal effects. In the p-type material, heat energy actually knocks an occasional electron out of its orbital, and then it's free to move around under the influence of the electric field supplied by the external voltage source. Since the p-type is connected to the negative supply, then the electron accelerates toward the junction and can cross the junction and then is attracted to the positive supply. Thus you get a little bit of current. This current is usually incredibly small, but it does depend a lot on the device, and it might be in the picoamp range or the nanoamp range, but in general they will be very small. Since this current is primarily due to heat energy freeing up mobile charge carriers, this reverse saturation current is very dependent on temperature. Now, by the way, you can make a similar statement about the N-type and holes being freed up, but the situation is quite analogous. Now, interestingly, this reverse saturation current is almost independent of the actual external voltage generating that reverse bias, except at extremely low voltages, or unless the voltage gets large enough for something a little more interesting to happen. There are two primary things that can increase that current. One is called Zener breakdown, which typically happens below about 5 volts, and this involves tunneling of electrons, and this is not the type of breakdown we're concerned with here. The other effect is called avalanche breakdown, and this typically occurs above 5 volts. In avalanche breakdown, when a thermal electron is freed up, it's then accelerated to a high enough energy by the external source that it can bang into another atom, knocking another electron free, which is then accelerated, which can then bang into another atom, knocking another electron free, and of course each time an electron is knocked free, a hole is created. This produces a cascade effect. The current can get very large very rapidly, and unless you do something to limit the current, the junction can get so hot that you destroy the device. So in general, if you're trying to run a device in avalanche breakdown mode, then you would put in some sort of additional component or components to limit the current. We'll see that in a moment. Now, where does the noise come from? Well, the thermal effects that knock carriers out of their orbitals so that they're free to move, first of all, is a random process. It doesn't happen uniformly. You don't get exactly the same number of charges knocked out of orbitals every yoctosecond. and the collisions of those carriers with other atoms, thus freeing up more mobile charges, is also random. So what we've got is this tiny little noise signal. Now this noise signal does have the properties of white noise. It does have a fairly flat frequency distribution, at least at reasonable frequencies. But it's riding on top of a very large, comparatively, DC offset. Since we want a noise signal with about a 5 volt amplitude, this means we're going to have to amplify the heck out of this little few millivolt noise signal. Unfortunately, it's got about a 10 volt DC offset, and if you even multiply that by a factor of 1.5, you're going to hit the saturation voltage of your operational amplifier, and you're dead in the water. We're going to need a gain of probably over 1,000. So we've got to get rid of the DC offset. To look at a basic circuit for generating this signal, usually you will probably use a transistor instead of a diode. They typically will generate a better noise signal. And it doesn't matter whether you use PNP or NPN, and you can test different ones and see which ones give you the best noise signal. But here I'm using an NPN. And remember, we need to do something to limit the current, so I will put a resistor from our positive supply, plus 15 volts, to the emitter of the transistor, and then I'll ground the base. The collector is simply not used. We're only using the emitter to base junction. The signal that appears at the emitter, like I said, is a tiny little noise signal of a few millivolts riding on top of a large DC offset. Now with the 2N3904, I've tested several of these, and the DC offset for these has all been close to 8 volts. That's sort of immaterial. It doesn't matter whether it's 8 or 10 or 9 or 7 or whatever, but you're going to have to get rid of it. In order to get rid of it, you simply add a single pole high pass filter to it. And note that the capacitor acts like an open circuit to DC, so the DC can't get through and the noise signal can. In the next video, we will discuss the cutoff frequency of this filter and how you go about selecting that. But this is our basic noise source. And then we'll take the output from this and we'll amplify the heck out of it, and there are a few other things we have to do, and eventually we'll have a white noise signal of about 5 volts amplitude. This signal can then be processed some more to give us other flavors of noise. In the next video, we will look at the details of a white noise generator.